Alright, so in today's lab, we're going to demonstrate how polymers behave using two foam materials, regular slime and bouncy slime. So using these, we're going to show you how changing the recipe affects the material's response to forces over time, revealing their viscous and elastic properties. Okay, let's begin with regular slime. For this, I dissolved 1/2 tablespoon of borax and 1/2 cup of warm water, and then in a separate container, I mixed another half cup of PVA-based glue with 1/2 cup of water. So when we combine these two mixtures, the boron ions in the borax formed cross-links with the polyvinyl alcohol in the glue, turning our liquid mixture into a stretchy, cross-linked polymer network. Alright, now let's see what happens when we put this regular slime through different conditions. Alright, so the first test we're going to do is rapid deformation, where we're going to pull apart the slime very quickly. So as you can see, the slime broke very easily, and this is because the applied force is very fast and the polymer chains don't have enough time to reorient. And in this scenario, the material behaves like a solid and snaps suddenly. This illustrates the elastic nature of polymers when there isn't enough time for viscous flow. So next, we're going to observe what happens when we pull apart slime slowly. So I'm going to reset the slime a little bit. Just like that. And pull it apart slowly. So as you can see, over a longer time scale, the polymer chains have the opportunity to uncoil and slide past each other. As a result, the slime stretches smoothly, showing its viscous liquid-like behavior. This shift in behavior from solid-like to liquid-like within a time interval is a direct demonstration of viscoelasticity. Finally, after stretching the slime to a fixed distance, let's say for example here, we hold it there. Over time, the force to maintain that stretch decreases as the internal stretch relaxes. This decrease happens because polymer chains gradually adjust themselves, reducing the internal resistance despite the constant deformation. Okay, so each of these behaviors, whether snapping under a fast pull or stretching under a slow one, demonstrates how the same polymer network can be both elastic or viscous depending on the rate at which you apply the force. So for the second part of our experiment, we'll be making a bouncy ball. I already made it here, but to make this, we adjust the recipe to increase the cross-linking. And to do this, we mix 3 tablespoons of borax with 1.5 cups of water, and then directly add 3 tablespoons of glue into the solution. By doing this, there are more boron ions available, meaning the cross-link density increases and the polymer chains become more tightly bound. So let's see the effect of this higher cross-link density with a couple of tests. So once again, starting off with the bounce test, when we drop the bouncy slime, we see that it bounces very high and deforms very little, especially compared to the regular slime, which barely bounces. So this behavior indicates a higher Deborah number, meaning that on our observation timescale, the material behaves much more like an elastic solid, storing energy and releasing it efficiently. So now let's compare the regular slime and the bouncy ball side by side when we leave it on the table. Alright, so as you can see, the regular slime shows significant deformation and flattens over time, a liquid-like response with a lower Deborah number. In contrast, the bouncy ball remains firm, highlighting its solid-like elastic behavior due to the increased cross-linking. Alright, so in summary, our experiment shows that polymers like our slime can behave both like a viscous liquid and an elastic solid depending on how fast they're deformed. When the force is applied quickly, the material reacts elastically, while when it's applied slowly, it flows viscously. By increasing the cross-link density, we can shift the behavior to create a firmer, more elastic, bouncy slime with a higher Deborah number. Thanks for watching.